Page 9 of the fault tolerance notes. Let's apply the convergence algorithm to see how it works. So let's just say we've got 4 clocks and our epsilon is 1. And so let's say that the 4 clocks start synchronized perfectly at time 0, and at time t equals 1000, at this point there's no problem yet. So they are all still more or less in agreement on what the time is, even if not perfectly. So what the different clocks read is C1 reads 999.6, C2 equals 999.8, C3 equals 999.9, and C4 equals 1000.3. So they're all within 1 epsilon of each other. And so now they need to do a calculation to update their time. So each clock will tell the other clocks what they read, and so the calculation will be the same for all of them, because they won't be excluding any faulty times or times that don't agree with them. So clock 1 will calculate 999.6 plus 999.8 plus 999.9 plus 1000.3 all over 4 gives us 999.9. And each of the other clocks will end up doing the exact same calculation, and so they'll all synchronize to time 999.9, which is fairly close to the actual time. Now, let's just say time has progressed, and at time 2000, and they don't know what the exact time is, but this is when roughly at time 2000 they're synchronizing again. At this point, C1 is faulty. It's fallen further behind, and it's no longer in agreement so much with the other clocks. So we've got C1, C2, C3, C4. We've got the time that's read, and so what we see is 998.6, 1998.6, 1999.5. So clock 1 and clock 2, they are within epsilon of each other. Clock 3 reads 2000 exactly. It's within epsilon of C2, but not of C1. So C1 and C3 are disagreeing, and C4 is 2000.2. So it's in agreement, it's within epsilon of C2 and C3, but not C1. And so now each of them is actually going to end up doing a different calculation to update their time. So let's write each of those out. So clock 1 will use its own time. It will use the time that is reported by clock 2, but when it receives the time from clock 3, it's going to apply the convergence algorithm. It doesn't know which clock is faulty. It doesn't know that it's faulty. So it's going to replace clock 3's time with its own time. So this is the convergence algorithm in action. And then when it receives clock 4's time, that is also not within epsilon of its own time. So it will replace that with its own time. Divide that by 4, and we get 1998.825. We've got to do this three more times. So clock 2 will accept the time from clock 1. It's within epsilon. It will use its own time. And then clock 2, 3, and 4's time is also within an epsilon of it. So it will use both of those. And we'll come up with an average of 1999.575. Okay, clock 3. When it receives the time from clock 1, it's more than an epsilon away, so it's going to substitute in its own time for clock 1's time. And the rest of the times that it receives will be within an epsilon of it. So it'll use clock 2's time, it'll use its own time, it'll use clock 4's time, take the average, and we get 1999.925. And lastly, clock 4 will also substitute its own time for the time that it receives from clock 3, but it will accept the times from clock 2, from clock 3, and from itself, and will come up with a new time of 1999.975. So each of these 4 clocks will update their times with these 4 different times. So they're not perfectly in agreement, but the non-faulty clocks 2, 3, and 4, we would hope that they more or less agree with each other, and over time their values will come closer together, whereas C1 will just continue to drift apart. So the average of these 3 is 1999.825. Now, something I've been asked before is, what if C3 and C4 excluded C1 instead of replacing it? So, for example, the C3, the new time, would be, we would leave out clock 1's time, so just nothing there, but it's just the other times. So 1999.5 plus 2000 plus 2002 all over 3, that equals 1999.9. Then the average of C2, C3, C4 would be equal to 1999.792, which is worse than the average above there, the 1999.825. So what happens is that clock 2 is being pulled away by clock 1, the faulty clock, and we need clock 3 and clock 4 to compensate for that by substituting their own times for the faulty one, and it will pull the overall average closer to the correct time. The proof for this is quite complex, but you can look up the paper and check it out if you're interested. One of the things from the paper is that this algorithm works if n, which is the total number of clocks in the system, is greater than 3d. So n is the total clocks and d is the faulty clocks. So for example, if d equals 1, then n must be greater than 3, so any value, so n equals 4, 5, and so on, then the algorithm will work. If it's less than that, if it's 3, 2, then it won't be able to correct for that one faulty clock. So as you increase the number of faulty components, you have to have more and more correct components.